Hello students, welcome back. Let us continue with what we are doing my last class. So in last class, we were discussing a particle moving in a circular ring. So we have a circular ring, say a circular ring, and a particle is moving in a circular ring, and the radius of the ring is capital R. And we told that the wave function of this particle are given by psi x equal to e power iota kx and one normalization constant. This was the wave function of this particle when we're moving in a circular ring. We have seen yesterday, and now I put it here k here. And we have also seen that physical observable like momentum, angular momentum, energy is also quantized. So we have seen that k was equal to 2 pi n L, and similarly if I write L is equal to here 2 pi r, so I can say this is equal to 2 pi n, and this is your 2 pi r, this is cancelled, so this is simply k is equal to n by r. And if I write the momentum, so momentum is h cut k, that is 2 pi h cut n, 2 pi n h cut upon L, and this also can be written as a n h cut upon r if I write L is equal to 2 pi r. Similarly, if I want to write the angular momentum, so angular momentum is simply p dot r mvr, which is equal to nh cut. And if I write the energy En, so energy can be written as a h cut square k square 2m, so which I can write as a h cut square. K is this one. I'm writing directly in terms of r. So energy k become n square upon 2m r square. So this is so these values are quantized. This is the one thing. And now second thing is the wave function. Okay, so what is the wave function? So let me write now this wave function. This wave function also can be written as a, say, this wave function also can be written as in terms of momentum. So if I write in terms of momentum, this wave function become L, I'm writing as a 2 pi r. You can write L also. This becomes e power iota p upon h cut x. And I can also write this wave function in terms of this number n. So we know what is k. K is your n by r. So this become 1 upon root L e power iota. K is n by r x. And this also can be written as a 1 upon 2 pi r for circular ring, 2 pi r e power iota and r x. And this is the simpler form, remember. So I take these are the wave function when particle is moving on a circular ring. This is my wave function. You can write this one also, this one also. You can use, instead of n by r, you can use the value of p also, 2 pi h cut n l. So these are the forms. So this is simple to remember. So I am writing in this manner. Now let us discuss what happens. Say I'm taking the next page. So I have now psi, and this is my 2 pi r e power iota and r by x. Now, if I say these all are the possible state of the particles, when a particle is moving in a circular ring, these are the all the possible state. If particle is in psi1 state, psi1 state, say psi1 state, then n is 1, n is 1. So my p will become what? P is what? P is your n h cut by r. Now n is 1, so my p become h cut upon r. Or if you want to write in terms of L, so 2 pi r is L, so this become L upon 2 pi, so this become 2 pi h cut upon L. So my momentum become this one. Similarly, if I write with the particle in state 2, in that case, the probability, then the momentum will be 2h cut upon r, 2h cut upon r. And if you want to write in terms of L, so this becomes 2h cut, and this is again 2 pi r is equal to L. So L upon 2 pi, so L upon 2 pi. So this becomes 4 pi h cut upon L. Similar way, if I want to write psi 3 and so this will be state 3, P3 will be 3 h cut upon R, or in terms of L, this will be 6 pi h cut upon L, so on. Similarly, you can write about the energies of the state and you can write the angular momentum of the state. So now these are the possible momentum values when a particle is moving in a circular ring. Now the question is, what is the probability that if I want to measure the momentum of the particle moving in a circle, what is the probability that I will get this value or this value or this value? Okay, for example, say so let us take one more page now. So for example, say I'm taking a rough example. Say you have a say a rod of say length L, and this rod is say moving in a xy plane. So this is the x plane, this is the y plane, and this is moving continuously moving in this plane. And I want to know the state of this is this rod. Now here state means I want to know what is the angle it's making with the x-axis. It's continuously moving. I want to measure this angle. What is this angle? So I will stop some time. That time I will know at what angle it is. So when you do the measurement, only that time you know the state. So I'm repeating again. I define the state of this rod as an angle. What is the angle it is making with the x-axis? Now this rod is continuously moving, and I have a instrument or device which can measure this angle with 1 degree accuracy. So that means if I can measure this angle with 1 degree accuracy, so there are total 360 possibilities states. Either rod can be at angle 1 degree, 2 degree, 3 degree, 4 degree, 5 degree. So if I can measure the angle with a 1 degree accuracy, so I can say there are total 360 states because there are total 360 degree. Similarly, if I have a device which can measure this angle with a half degree accuracy, then I can say I have a total 720 states. A rod can be in any 720 states. It's continuously moving. Now, similarly, if I can measure the angle with a 1.1 by 4 degree accuracy, then this become 1440 states. This rod can be in 40 states. So exactly in which state rod is that only can be known when I try to when I go for measurement. And now here, because this is the case where every state has a equal probability, the rod is continuously moving, and I want to find which is the state. What is the angle this rod is making with a x-axis. So anytime if I do measurement, all possible angles are possible. That means this is the equal. All states are equally probable. But it is not the always case. Now, for example, we have a state here. We have a state here psi n 1 upon 2 pi r e power iota n by r x. So what is the probability that this is state 1, state 2, state 3 that we want to calculate? Now, if I calculate, say, psi n star psi m, okay, if I calculate this one and in a limit 0 to pi r or 0 to L dx, what I can write, I can see this is equal to 2 pi r 0 to 2 pi r, and now this is become e power n minus m upon r x dx. Now this has a value delta nm. Delta nm, why? If my n is equal to m, in that case this term becomes 0 and dx is 2 pi r, so 2 pi r cancel, and this integration has the value is equal to 1. This integration has the value 1, and if n is not equal to m, then what will happen? This is the e power iota x type of function, and we can always write this function as the cos x plus sin x form, and we know the average of cos x and phi x is 0. So this, when n is not equal to m, this integration will be 0. That's why I written this is a delta n. So this is the property of these states, that these states are orthonormal. They are normal to each other, like a vectors. Two vectors are if normal to each other, their dot product is 0. Similarly here, if the two states are normal, their inner product, that is their inner product, the function, their inner product will be 0. So these are the orthonormal state. This is the property of this function. Now my aim is to calculate the probability of a state n. So let us go for now calculate the probability of states. So there's one more thing I can do, because these are sine cos type of function, harmonic functions, and we know from the Fourier series I can write any periodic function psi x as, कैसे लिख सकते हैं इसको? I can write summation a n psi n. I can write any function in terms of n. So if you know the n, you know the so a is the what? Amplitude. Any function can be written expanded in terms of any periodic function. So if I have a circular ring and if I define a function, say a function here psi x, so that psi x can always be expressed as a superposition of these functions. This is the one thing. And now how to calculate an? Psi n we know. How to calculate the an? So probability of getting n is equal to a n mod square. Now how to get this a n? For that we know we can use concept of what we do in vectors, or we do in Fourier series, which is called Fourier trick. So what I can do now, suppose I have a psi x summation, we have an psi n x n, and now if I if I want to get value of an, so sorry, I want to get value of an. So what I can write? I can write this is psi n. I'll take the component of psi n in psi x, that is psi n psi x dx between 0 to 2 pi r. If I calculate this one, so what I'll get? 0 to 2 pi r, and now we have a psi n star, and here we have a an psi n x dx. And just now I told these wave functions are orthonormal, so only the component of this summation will survive will be sin x dx. And so if I solve this one, so this if I solve this one, this will be, I know this psi n, so this will be what? This will be 1 upon 2 pi r, 0 to 2 pi r, and all other terms will be 0. So we will left only with the an dx. If I integrate this one and open this one, only the term will be left this one, and this will give me is equal to 2 pi I can say an. So in this way, so this if you want to find the an, you have to do this integration. So once I know the an, I know the probability of state n, or probability the momentum will be n, will be equal to what? A mod of an square. So let us take one example. Say I'm taking a simple example. Say my psi x this time. Say my psi x, we have a circular ring, and I am taking a periodic function here. Remember, this should be periodic. So I'm defining a periodic function, say n, or say a, say cos 3 pi x upon L. I'm defining a here. So how can I solve this one? So say this is a function, and now let us normalize this function. So if I normalize this function, so this will be psi star psi, that means mod of a square cos square 3 pi x upon L, which should be 1. And if I calculate now the value of normalization constant a square, this can be written as a what? Cos square can be written as a 1 plus cos 2 theta, 1 plus cos 6 pi x by L by 2 dx. And I am taking a length, say 0 to L. You can take 0 to 2 pi r also. 2 pi r also. Then what will happen? Mod a square dx. This will give you L. If I solve this one, this will give you L minus 0, x minus 0, and this function is will be in a the average of this function 0 to 2 pi 0 to L will be 0. So this is equal to, so my a will be say root 2 by L. So my a is root 2 by L. Okay, so I can write now my function is psi x root 2 L cos of 3 pi x upon L. And this function can be written as, say, I can write 2L. So this will be 2 pi r. So this will be 1 pi r L equal to 2 pi r. And this will be cos. Cos I can represent because I want to bring it in exponential form. So cos I can write as a e power iota kx 3 pi x upon L plus e power minus iota 3 pi x upon L 2. So this becomes 1 upon pi r now this I can also bring in terms of n. And what I'm now doing, because we know our function, so I'm writing here 1 upon root 2 here, and I'm writing this as the e power root 2 pi r, and this is 3 pi xl. So if I write L equal to 3 pi x and L is 2 pi r, so pi cancel. So this becomes 3 by 2, 3 by 2 xr. And similarly, this term become minus iota 3 by 2 x upon r root 2 pi r. Now here, what is the value of n if we compare with our function? If I compare, our function was 1 upon root 2 pi r e power iota nx upon r. This is my function. So here n value is 3 by 2 and minus 3 by 2. So only these two values are possible. If this is a function, if I define this function in a circular orbit, only two states are possible, and their probability, if I want to find their probability, so probability of is a function and it's a probable, and this is the value of an for each, both are same. So I can write this function as a 1 upon root 2, and this function is psi n, so I'm writing this is psi 3 by 2, and plus 1 upon root 2, and this is my psi minus 3 by 2. Okay, or instead of, if it's coming to root, you should take it as some even number, say 6. If I write some even number 6 here, then what will happen? This will become 12. So this will become 12, and this becomes 6. This becomes 6, 6, and this becomes 3, and this also becomes 3. So now I can write this is the state with n equal to 3, and this is the state with n equal to minus 3. Minus 3. So probability of getting, say, 3 is an square, is 1 by 2. Probability of getting minus 3 is also 1 by 2. Okay, that means if we are in state psi 3, my momentum will be what? My momentum will be P3, which is momentum was what? N h cut upon r. N h cut upon r means here 3 h cut upon r, or 3 h cut 2 pi 2 pi l l upon 2 pi l upon 2 pi, because 2 pi r is equal to l. So r equal to l upon 2 pi. So this becomes 6 pi h cut, 6 pi h cut upon l. So the moment, there are two momentum values are possible for this wave function, 6 pi h cut upon l or minus 6 pi h cut upon l. Both have a probability half and half. Similarly, you can now do it for the angular momentum. Angular momentum values are 3h cut, 3h cut, and minus 3h cut. Angular momentum values. So this way, so what I'm trying to say here, that here, if I want to write a general state, so this is always possible. So here what we have shown, that I can expand any function in terms of the eigen states of momentum. Okay, so, and if we expand this one, then calculations becomes easy. Suppose I want to calculate the probability, or I want to get the momentum value, anything, any calculations, that becomes simpler. So this is called what? This is called spectral decomposition. Spectral decomposition means, if it is possible, if we can explain represent any general state of the system in terms of the any operator or any observables eigen states. So here we have in last slides we have seen here. So we have expressed psi x in this particular case as a sum of eigenstates of momentum wave function. And the eigenvalues, we told what are the eigenvalues we got. The eigenvalues we are n, because the function is iota n x upon r. So getting the possibility of this is the eigenvalue, or if you can write in the terms of momentum, you can get the momentum eigenvalues. You can get the momentum eigenvalues. And so these are the spectral terms. Spectral terms means in which kind of states a system can be. That's are the spectrum, and these are their eigenvalue, and this is called spectral decomposition, or writing any function and any general state of any function in terms of the eigenstate of any operator observable. Okay, so that is in this class. We'll continue with some more example on a circular ring in next class. Thank you very much.